Hello viewers, welcome back. In this video lecture, we are going to talk about how we can identify the diastereomers and the meso compounds. To understand this topic, we need certain fundamentals how to identify the absolute configuration R and S. That we already learned it in the previous lectures that I posted in the description link. Please go through that. So that is most fundamental thing to understand and solve this concept, how to differentiate enantiomers, diastereomers and the meso compounds. Okay, that is most very important thing. Please learn that. Here first what we have to do is, here I given some compound. You see there are 4 carbons. So first I number it. So this is the 1 and this is the second carbon and this is the third carbon. Okay, and this is the 4th carbon, because the bromo comes in the one. That's why we have to know the nomenclature, that we have to give very carefully. Okay, why I did it in the beginning, to avoid such a confusion. Okay, some confusion may come, so why I numbered the chiral centers, okay, with the appropriate carbon number. Now listen carefully. Now we are going to identify the absolute configuration of this second carbon. Okay, as I taught you how to do that I've given in this absolute configuration, how to solve that. So use that technique. So whatever this wedge bond, that you have to put it in this. So before that you should view that in this certain this view, angle of view, okay, that I mentioned in that absolute configuration video lecture. Please go through that. First step is angle of view. The second step is you have to put it in the plus symbol and assign the groups. So wedge one I should put it in the top of the vertical line, and the dash one like this. So this is the angle of view. So in the right hand side this is the group. So like this, connected to like this, and this is the one is CH3. According to the sequence rule, the bromine is the first, it will get the first priority, and the second priority. Both are carbons. You see CH3 is also, this is a carbon, and CCl, but the second atom is the chlorine. So why? So this carbon will get the second priority, and the third one will be the methyl. So it is going by this way. So it is rotating in the anti-clockwise direction. That means this is 2s configuration. Similarly you should find out the third carbon, that is the chiral center. So again you put it in this one. So first the angle of view should be like this. Okay, for this one we should like this. Okay, so because this should go away from the viewer. So wedge bond is on the top of the vertical line, and dash bond is bottom of the vertical line. So according to this view, this methyl should be in the right hand side, sorry, left hand side, and this whole group should be in the right hand side. So like this. So CH3, hydrogen and bromine. Okay, so this is the first one. The second one, according to the priority, so which I already mentioned, so it goes again by this way. So again this is anti-clockwise, that means this is S configuration. So that means 2s, 3s. Similarly, so what you can do, so this is 1, 2. Now this will be the 2, and this could be the third carbon. Okay, so this could be R configuration. So by applying the same way, you do like this. So the bromine should be bottom, and that hydrogen should be on the top, the methyl is on your right hand side, the remaining group is on the left hand side. Okay, so like this. So now this is the first position, this is the first priority, and this could be the second, and this could be the third. You see, it goes by this way in the clockwise. That means this is 2R. And similarly, by the same way you can find out, you will get this 3R. As you know that for this molecule is having two chiral center. This is the mirror image. Okay, so this is the mirror image. So I'll make this is the first one, and this could be the second one. Okay, so according to the calculation of total number of stereoisomers, the formula is 2 power n. N is number of chiral centers. This is 1, 2. That means total we should get 4 stereoisomers. So 2 stereoisomers we got like this. Again, how we can get the 2 more stereoisomers? So what I did is, here I swapped, you see, listen carefully, this one, the chlorine, this whatever this one, I changed this chiral center, I swapped it. Okay, so in this case what will happen? The sequence rule will be the remain same, sequential order, but this position is getting changed, the spatial arrangement is getting changed. As a result, this one will be this almost same, but you should be very careful to assign the absolute configuration, because this chiral center is not getting changed. You see, this second and this third carbon. Okay, so that means this will be the remain same. So definitely you should have the 2s, and here this one is changed. You see, this is dash and this is wedged one, the chlorine. So definitely this will get changed. If it is 3s, then we will get the 3r. If you want to confirm it, you can apply the method, the trick, whichever I taught it in the absolute configuration, or here also I taught you. So you can apply it and you can confirm it. Okay. Similarly here, so this is the third isomer. Okay, and this is your fourth isomer. So this is the mirror image for this one. The fourth is the mirror image for the third one. So this is the opposite to this one, the second. You see, so this is the second one, and this is could be the third one, third carbon chiral center. So we didn't change the bromine here. That means, so this should be here as 2R. That means here the chiral center will be the definitely a 2R. What about this third one? Third one is changed. You see, here the chlorine is dash bond, here it is a wedge bond, here it is 3R. Definitely we should get opposite 3. Yes. Now we find out this one absolute configuration for the 4 isomers. Now we are going to conclude it. Listen carefully. Why I asked you to number very beginning means that is important. Sometimes what we do, if we don't number it, so we may get confusion. So in order to find the proper mirror images, so 2s, we have to compare this to the second carbon and second carbon. Here 3 and 3. You see, this 2s is 2r and 3s is 3r. That means this 1 and 2 are enantiomers. Okay, enantiomers. You see, compare the 3 and 4, 2s, 2r, 3r, 3s. That means 3 and 4 are enantiomers. What about 1 and 4 and 2 and 3? You see, so let's take 1 and 4. You see, 2s, 3s, 2s, 2r. Here it is an opposite. And 3s, 3s. You see, these are non-mirror image. 3s and 3s are non-mirror image. That means these are 1 and 4 are diastereomers. Okay, diastereomers. What about 3 and 2? Is it 2s, 2r? It is opposite. Fine, that is mirror image. But here 3r, 3r. That means 2 and 3 are diastereomers, that because non-mirror image. Okay, you see 1 and 3, you see 1 and 3 also, 2s non-mirror image, but 3s 3r. Even if there is one non-mirror image, that means you should consider it is a diastereomers. So 1 and 3. Similarly 2 and 4 are diastereomers. Okay, same thing. So this is how you should find out the diastereomers and enantiomers. If it is an opposite non-superimposable mirror image, then we call it as an enantiomer. You see, listen carefully, 1 and 2, 2s 3s, that 2s 2r, 3s 3r, that means it are enantiomers. You see 3 and 4, 2s 2r, 3r 3s, that means 3 and 4 isomer relations are enantiomers. Okay, so in conclusion, diastereomers are non-mirror images of each other and are not superimposable, which are called as diastereomers, like this, you see, which I showed here, 1 and 3, you see, 2s because non-mirror image. If it is mirror image, means it should be R and non-superimposable, that are called as enantiomers, like 1 and 2, 2s 3s, that is 2r 3r, likewise. Okay, in conclusion, diastereomers are non-mirror images and non-superimposable. Okay, these are called diastereomers, but enantiomers are superimposable, non-superimposable mirror images. Okay, non-superimposable mirror images are called as enantiomers. Okay, so this is the way how we can find out or differentiate the enantiomers and diastereomers. Now let us take the same thing. Here I take the same thing. Okay, you see here the same compound, here this chlorine. Okay, so what you can do is you can take this compound, you find out this absolute configuration like this, the same way how you can find out the chlorine. Here this is 2 and third one, so chlorine should be go top and like this, and this is the methyl and Cl, and this is CH3 and this is the hydrogen. So the first one will get the chlorine connected, and second one this is, and this is the third one, so it goes like this. So this is going in the clockwise, that means 2R. What about this compound, this 3 carbon? So we have to view in this direction. Okay, so that means the chlorine should go not chlorine, because chlorine is a wedge bond. So hydrogen is on the top, the chlorine is on the bottom of the vertical line. So if you are viewing in this angle, the methyl group should be in the left hand side and the remaining part should be on the right hand side. Okay, so Cl and this is CH3, so H. So 1, this is the 2 and this is the 3. Again this is going on this like this. So what it goes, it is going in the which direction? Anti-clockwise. That means this is S configuration, 2R and 3S. Now you listen carefully. These are 2 chiral centers and we find out each chiral center absolute configuration. You see, observe carefully, it is, the molecule is plane of symmetry. You see, 1 because equal halves, both halves are containing equal, both are containing this carbon, chlorine, hydrogen and CH3. You see, both are equal halves, but one half is R configuration and another is S configuration. What will happen? Suppose one of the half is rotating in the clockwise direction and other half is rotating in the anti-clockwise direction. That means that net optical rotation will be 0 due to the internal plane of symmetry. So this type of compound is called as meso compound. So why? This optical rotation is 0. So in short, so the stereoisomer which is having chiral centers, but it will act as an achiral when this will not show optical rotation or optically inactive. Such compounds are called as meso compounds. Also, that optical rotation is due to the presence of internal plane of symmetry, because that cancel the rotation. Okay, so these are called meso compounds. What about here? The same thing, you see, the chiral center is same. That means this will also, we will get 2R. But what about this one? This chlorine is here wedge bond, sorry, dash bond. Here it is in the wedge bond. That means here it is 3s, means then we will get here 3R. So there is, though it's having plane of symmetry, but we are having not opposite this configuration. Okay, that means it will not cancel this optical rotation. Definitely this compound will be the optically active. So I will conclude it. Please listen carefully. When we should consider a compound is meso compound, first we should find out the absolute configuration, okay, as per the trick I taught you. Then you check it whether there is a plane of symmetry, how both of should be equal. Okay, you see, both are having equal offs. Whatever the groups we are having, the same groups we are having, but their optical rotations are opposite. That's why this will cancel each other. The total optical, that's net optical rotation will be the 0. That's why this is optically inactive. But these compounds having chiral center, please remember that these compounds are having, meso compounds will have the chiral center, but it will be considered as a chiral due to optical inactive. That's why there is the relation between the chirality and optical rotation. It is not necessary all the chiral compounds is necessary to be optically active, but all the optically active compounds are chiral in nature. That we should remember. Okay, all the optically active compounds are chiral in nature, but reverse is not necessary. Okay, these are about the meso compounds. I hope you understand this lecture. Please subscribe and share it if you feel this video lecture useful. Thank you very much.